Let's start with this question. See the first question. Calculate the entropy change for 1 mole of diatomic ideal gas undergoing for the process A to B as shown in the diagram. Okay, so let me just quickly copy this and we'll do it in the next page. Yeah, here somewhere here I can copy. Right, let's see this everybody. Calculate entropy in this case in a diatomic ideal gas. Okay. So how I would start, first I will check uh, being a diatomic ideal gas. So first I'll check out what is the CV and CP. CV is 5 by 2 R and CP will be 7 by 2 R. This is the first thing I'll clear it off. Okay. Second thing, because it is for an ideal gas, the general formula is NR ln uh, V2 by V1 plus NCV ln T2 by T1. Okay, this is what I'll have it. And now, starting with A, because you know that when it comes to A to B here, the process goes this way. So this is a pressure term, this is a volume term. Okay, and initially volume and pressure is known, so this temperature term can also be represented in terms of pressure and volume. Let me do that as well. So because P1 V1 is equal to nRT1 and P2 V2 is equal to nRT2, so I could write that T2 by T1 is equal to P2 V2 by P1 V1. Okay, so let me put that here. Delta S will be equal to NR ln V2 by V1 plus NCV ln P2 V2 by P1 V1. Okay, this is what you need to do. Clear? You don't have to worry about how the process is happening. Got it? Reason being, uh, entropy change is an state function, so you don't have to worry about how the process is. We just need to know the input of the initial and final conditions. So now let us put the values here. Number of moles, you can see we are doing it for 1 mole, so 1 into R ln V2 by V1. So V2 being 4 liter by 1 liter plus 1 into CV being 5 by 2 R into ln P2. P2 being 1 and V2 being 4, and here it is 1 and 2. Okay, so that makes it 2R ln 2 plus 5 by 2 R ln 2. So R ln 2 comes common. So therefore this is 4 plus 5, 9 by 2. So 9 by 2 R ln 2. This is what you should get. Correct? So 9 by 2 is 4.5 into R into ln 2 value is given, I guess. Yeah. So that is given as 0.7. And in fact, the R value is also given in calories. So 2 will get cancelled. So 9 into 0.7. So how much we get? 6.3. So 6.3 joule per Kelvin. That will be the value of delta S. Is this clear? I hope all of you got this point. How to solve it? Yeah. See the second one now. Read out the second one. A cylindrical container of 44.8 liters divided into equal moles, right? Into two sections. separated by a adiabatic frictionless piston. This one is adiabatic frictionless piston. The initial temperature and pressure of the gas in both the sections is 27.3 and 1 atm, in here also and here also. Now the gas A is slowly heated with the volume of the section B becomes 1/8 of its initial volume. So here this volume got reduced to 1/8 here. Okay, because gas will start expanding in A. Find the change in enthalpy of section A. This is the question asked. Okay, both side there is monoatomic gas and uh, so we need to find out the enthalpy for A. At 1 atm and 0 degrees, we know that this is the STP value given to us. Correct? So you would notice that initially the volume is given 22.4 liters and also the pressure is 1 atm and temperature is 0 degrees Celsius. Okay. Have you noticed something? The word slowly is used. Slowly means you are doing in a reversible manner. Got it? So that there is an extremely slow movement, quasi-static process this is. So therefore, reversible adiabatic conditions are applicable here. So reversible adiabatic conditions are applicable. Got it? Now, if that is applicable, can I say that T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1, isn't it? So from here, let's say we'll try to figure out what is the final temperature, that is present in section B here, correct? So because that is the volume which is getting decreased. So let us apply it on section B. So T2 here will be equal to T1 into V1 by V2 raised to power of gamma minus 1. Okay. And therefore T2 will be equal to T1 into V1 by V2 is 8 units, because V2 is getting decreased by 1/8 of its volume. So that divided by gamma is 3 by 2. So 3 by 2 minus 1 is 2 by 3. Sorry. Uh, uh, how much it is? Gamma minus 1. Acha, gamma is 5 by 3. Sorry. 5 by 3 minus 1. So that makes it T1 into 8, and this will be 2 by 3. Okay. So initial temperature is 273 kelvins into, this is 2 raised to power of 3 whole raised to power of 2 by 3. So 3 will get cancelled, and 273 into 4. So it is 4 times of T1. This is what we have. Okay. This much is a temperature that is raised in B part. Okay. So on that note, how much will be the pressure raised in that case then? Pressure will be, because it is an ideal gas, initially if it was P1 V1 by T1, now it must have become P2 V2 by T2. So from there I can calculate what is P2, which is equal to P1 multiplied by V1 by V2 multiplied by T2 by T1, correct? So P2 will be equal to P1 into, and P1 is 1 atm. I'll just write down that as 1 atm into V1 by V2, we just learned it as 8, into T2 by T1, we just learned that as 4. So which means 32 atm is the pressure that is developed in section B. Okay. Now, do you notice something? Because it is a frictionless piston, the piston will stop when both sides the pressure becomes equal, right? So that means this P2 is the pressure of A, pressure of B, which is P2, and that is 32 atm. Okay. So the reason for finding out the pressure is the same thing, that the pressure on both sides will be same. Correct? Okay. And now, once you know how much is the pressure here, this is the pressure in section A. Okay. Now what will be the temperature in section A then? Okay, clear. Let's see how much will be the temperature in A. Hmm. Temperature in A. Is there any volume that has been raised up? Mhm. Hmm. Let's see how much is the volume that must have been increased here in A side, because Q is been provided here, heat is been given here. Then we need to check out how much amount of volume that is being raised here, because B side it is going and this much is the volume that has been occupied, isn't it? So now notice how much was the total volume earlier. So it was 22.4. Now it has become 1/8 of it. Clear? So that makes it, let me check out the calculation here. So 22.4 divided by 8. So 2.8. So final volume, sorry, final volume of B section is 2.8 liters. That is 2.8 liters. So which makes it final volume of A will be equal to how much? Okay. So out of that 22.4 liters, correct? So this much amount of volume is present for um, this much is the volume present is for A. So 22.4 minus 2.8. So that is 19.6. 19.6 liters is the volume which is covered by A here, plus 22.4 which is original volume. Correct? So 22.4 plus 19.6. So that is 42. So 42 liters is the volume here. Correct? So originally how much it has? It had 22.4. Now it had 42 liters. Is this point clear, everybody? Right. So now we know the final volume. Now let us calculate the temperature A in this case. So temperature A, earlier how we found that pressure term here, same way I can find out for temperature. So temperature of A, final temperature of A will be equal to P2V2, P2V2 by P1V1 multiplied by T1. Okay. So P2 by P1 is 32 by 1 into V2 by V1 is 42 by 22.4 liters, that multiplied by T1. How much is the T1 value? So let me put it as T1 only here. Okay, T1 is anyway 273. So 42 divided by 22.4, so that is 1.875 into 32. So 32 into 1.875 into T. Okay, so 32 into 1.875. So that is coming as 60. So 60 times of T. This much is the temperature that I was raised uh, in A. Okay, everybody, please check this question so far. This is the final temperature in A side, beta. Now we got the temperature in A side. Got it? Original temperature T1 was 273 kelvins. Now, if I know this, now I can calculate what is the delta H value. So delta H value that has increased in A side will be equal to NCP delta T. Okay. So number of moles which has been taken here is how many? Equal number of moles. So number of moles is not given, but pressure, volume, temperature is known. Okay. So in fact, 22.4 is given. You can clearly make out that at 180 and 0 degrees centigrade, there will be 1 mole only here. So therefore, it is 1 mole into Cp value. Because it is a monoatomic gas, Cv is this much. So 5 by 2 R into T2 is 60 T1 minus T1. So that is equal to 5 by 2 into R into 59 T1. So this is the value you will get. Okay. R is 2. So if I cancel out the 2 here, so 5 into 59 into 273. So that much in calories. What do we have? 273 into 59 into 5. Okay. So 80.5 kilocalories. This much will be the value. Done. Please check, everybody. It's a good question. And a very similar question was asked in JEE Advance, just 2 years ago. So please check it out. Try to understand the method in which you have to approach. Okay. Samyak, any doubt, beta? Good. Shauri, Utsa, Ishman. I hope all of you are following this question. Right. Finished. Shall we go for the next question, everybody? Let's see the third question. Read it out. The heat capacity of liquid water is given, while the enthalpy of fusion of ice is given as 6 kilojoules per mole. What is the smallest number of ice cubes at 0 degrees, each containing 9 grams of water, needed to cool 500 grams of liquid water from 20 degrees to 0 degrees, 20 degrees to 0 degrees? Okay. So how many smallest number of cubes that you can make? Each should be of 9 grams, which is needed to cool 500 grams of liquid water from 20 degrees to 0 degrees. Okay, guys, so try this out. This isn't that difficult, so I hope you should be able to figure it out. Okay, I'll give you a head start. Just start trying for a minute and then I'll start. Okay, so we can figure out easily that number of moles of water is 500 by 18. So which makes it 27.78 moles, right? And thereafter Q, which is equal to NC delta T. So 27.78 into 75.6 into 20 minus 0. This much amount of heat is what is being supplied. Okay. So this value is coming as 4964.48 or simply 41.96 kilojoules. Correct. Now you notice this number of moles of one ice cube is 9 by 18, which makes it 0.5. Okay, so Q of ice, right? Heat of ice that is lost is N into delta H of fusion. Okay, so N is 0.5 into delta H of fusion is given, I guess, yeah, 6 kilojoules, right? So that makes it 3 kilojoules. So 3 kilojoules of energy has been given out. So the amount of energy given and taken should be same, correct? So heat lost. So 4196 is the amount of heat that is been gained. And how much of the heat loss is n number of cubes into 3. So n value will be equal to 41.96 by 3, which is 14 cubes. Does that make sense, everybody? Very good. Now let's get on to the fourth question now. Yeah, let's try this one. Okay, I'll put that here. 5 moles of H2O at 373 kelvins and 1 atm is converted into H2O at 373 and 5 atm. Delta G for this process is how much? Okay, let me start this now. H2O liquid, it is trying to convert into H2O gas. Okay. So I need to figure out what is the delta G for this reaction. Got it? So you can start it in both ways here. You know that dg of both of them, that means small change in here, right? So usually we write dg of any pure substance is equal to vdp minus sdt. And since it is at constant temperature, this value will become 0. Got it? And if you write it for the products here, products has gases here. So therefore it will be n. Now suppose if at all I write this volume factors, notice this one thing. When I write d of delta g, that has to be volume of H2O in gases minus volume of H2O in liquid into dp, correct? This is products minus reactants, isn't it? Now tell me, volume of vapor compared to the volume of liquid, isn't it very much ignorable? This value can be always ignored. So therefore, I could write this as d of delta G will be equal to volume of H2O in gaseous state into dP. Now this can be considered like an ideal gas and you can write it as nRT by P dP. Now integrate them on both sides. So delta uh, G1 to delta G2 here, correct? So that is the, I mean delta, sorry, this one, if you integrate that, you will get it as delta G of the reaction, which is equal to integral P1 to P2 into nRT by P dP. Okay, so nRT will come outside and ln P2 by P1. So that's how we can get delta G is equal to nRT ln P2 by P1. And since it is at a constant temperature, we can also write nRT ln V1 by V2. isn't it? So either you can write it as P2 by P1, or you can write it as V1 by V2. Clear? Now check what are the factors that are given to us. You notice that the initially vapor pressure, how much it is, and now how much it is given. So therefore, pressure terms are given. We can use that formula directly. So delta G is equal to, and we are doing it for 5 moles. So 5 into R into temperature is 373, right? Into ln P2, final temperature, final pressure is 5, initial value is 1, right? So therefore 5 into 2, because we are writing it for in calories. So 5 into 2 into 373 into ln 5. Is the ln 5 value given? No, ln 5 value is not given. Acha, but the answer is given in ln 5 only. So let me keep it that way. So it is 3730 ln 5. So that should be the answer in calories. Right. So please go through it once, everybody. So make any doubt? Utsa, did you get that? Utsa, could you respond, please? Anna, did you understand this question?
Yes, sir.
Saida?
Yes, sir.
Right. Let's do the next one. Check out the fifth one now. This is a PYQ question. A very, very similar PYQ. I've just modified that here. Okay. This is a little difficult one. This has some concept of chemical equilibrium also. Okay. We will try to solve and see whether we will be able to solve with our given, knowledge, whatever we have gained here. If not, I'll explain it a little more in detail. Okay. So let us read it out. Let's read out and try to understand what is being asked, everybody. See, a substance A has the following variation of vapor pressure with temperature for its solid state and liquid state. Identify the options which are correct. Solid A. For solid state A, P is given this way. For liquid state A, P is given this way. Okay. Enthalpy of vaporization and enthalpy of fusion will be independent. Okay. These are the options given. Delta H of sublimation is given, delta H of fusion is given. So what are these terms? Basically here, let us assume that the substance what we are talking is about water. Just for sake of understanding, let us say that substance A is H2O. So one thing is given that H2O, when it is solid and existing as H2O gas, here we'll have delta H of sublimation. Similarly, H2O, if it is in liquid and it is in equilibrium with H2O vapors, then here we'll have delta H of vaporization. Got it? For solid, the variation of the vapor pressure, here this is the vapor pressure. So the variation of the vapor pressure is given in terms of this formula, 4 minus 2000 by T. While variation of vapor pressure here is given as 3.48 minus 1500 by T. These are the two things which are been given. Okay. P here the pressure is in actually mm of Hg. Here also mm of Hg. Okay. Now you just need to recall the formula from here. So if you can get the formula, that will be more than enough. Okay. Now where do we get this formula and how do we apply that? You know. if you notice it, uh, one thing from I'll try to derive from the thermodynamics whatever we have learned, considering we do not have much idea from equilibrium. Okay. One thing we learned that delta G is equal to delta G naught plus RT ln Q. This is a very standard formula that we will be using. Even if you do not know the derivation, we will be always using this formula. That is, how much is the free energy in a chemical reaction given that delta G naught, which is at standard values, plus RT ln Q. Q is called the reaction quotient, which decides whether the reaction in the forward direction or the backward direction. Okay. Now, at equilibrium, you know that at equilibrium, delta G will always be 0. So, which means delta G naught will be equal to minus RT ln Q. This will be minus RT ln Q. Now, delta G naught can be written as delta H naught minus T delta S naught, which is equal to minus RT ln Q. Okay, this will be minus RT ln Q. Sorry, not Q, Kp. Because now it has become uh, at equilibrium, so Q will become Kp. Got it? So this is what we have. Now can I write this? Ln Kp will be equal to minus delta H naught by RT and plus S naught by R. This is the equation we can write, isn't it? This is the equation we can write here. Okay. So in that case, can I write something like this here that ln, now what is Kp exactly? Kp will be equal to, Kp is the representation of partial pressures of the reactants and products. So which will be equal to partial pressure of H2O in the products. By reactant is liquid. So for liquid, we always assume, liquid or solid, we always assume this to be 1. So it is simply the pressure here. So the pressure here of water means it is vapor pressure. So this is ln P is equal to minus delta H naught by RT plus delta S naught by R. Okay. Now let me write this in log. Ln can be written in log as 2.303 ln P is equal to minus delta H naught by RT plus delta S naught by R. So if I take the 2.303 on the right hand side, that will become minus delta H naught by 2.303 RT plus delta S naught by 2.303 R. This is ln P. Now, this is a derived formula which we are supposed to use. Okay, now this formula is what we are supposed to use. Directly, I could have used this as a formula, which we will do it in equilibrium. But since we do not know how we got that, that's why I derived everything. Okay. So from here, you know that this is what we got. And now I have to just compare these values for both the cases. In the first case, if you notice, this is about sublimation, right? This is from solid to gas, sublimation. For sublimation, this will become ln P is equal to minus delta H naught of sublimation divided by 2.303 R into temperature plus delta S naught by 2.303 R. Now, as per the formula, you can see this 2000 should be equated to this one because this is the slope of the equation. So delta H naught sublimation divided by 2.303 R, that is equal to 2000 as per the question. So let me put this as equation 1. Thus in the second case, when you are comparing this one with this one, now this is liquid to gas. That means it is about vaporization. So this is vaporization by 2.303 R T plus delta S naught of vaporization. Here this is also sublimation by 2.303 R. Now, if at all I compare this one with the given equation here, so I would get this as delta H naught of vaporization by 2.303 R, that would be equal to 1500. So two equations, two unknowns. That's what we need to calculate. What is the delta H of sublimation and what is the delta H of vaporization? Okay. Now listen, sublimation and vaporization is known. Can I know this one also? That is H2O solid to H2O liquid, correct? Because in that case it will become sublimation minus vaporization. So that is called as delta H of fusion. So solid to liquid conversion is called fusion. So if I calculate sublimation and vaporization, we can automatically get what is the fusion part here. Okay, everybody, please try to derive it on your own and see, because this is something which we'll be using very frequently in the next topic as well. All right. So try to understand once and do it on your own. Okay. I'll give you 2 minutes, finish that part. Right. Let's see the sixth one. What does it say? Choose the correct options. Q is equal to NCV delta T is applicable to all substances during heating or cooling at constant volume. Okay. Q is equal to NCV delta T. This is valid for all the substances. It is not necessary only for solid, liquids, gases, nothing. It is for everything as long as you are not using it as delta U. Remember that. Okay. So that means if you are writing it as delta U is equal to NCV delta T, this is only valid for ideal gas. This is only valid for ideal gas. Got it? But otherwise, if you're writing it as heat that is being given at constant volume, yes, we can write it as NCV dt. Clear? So there is no problem in writing that. So first one is okay. Second one, NCV dt is applicable to ideal gas during heating or cooling at constant volume only. Okay. So if you are putting it at constant volume only, then this is the amount of heat that is being given. So that is also correct. This is the heat that is being given. Clear? Because Q is a path function. Remember, Q is a path function. That's why it has to be written at constant volume only. Okay, clear? Right. So next, check out what would happen to C in this case. Du is equal to NCV dt, that is applicable for real gases at constant volume. Okay, so this is also true. At constant volume, this is applicable for real gases, isn't it? Can you recall what is the formula with which we have written it for ideal gases? Okay. For real gases and ideal gases, if you recall, see, let me remind you what we have discussed earlier. If you notice that du can be written as dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dv. Clear? This is how we can write. And what is the uh, first equation? Dou u by dou v at constant temperature can be written as T into dou p by dou t at constant volume minus P. This is what we know. Okay. This is the equation of the state, first equation of the state. And this we know that can be written as NCV dt plus dou u by dou v in at constant temperature into dv. Clear? This is the value we have. Imagine if this value, if it is not operating at constant volume, if it is not operating at constant volume, then for real gases this factor will exist. But if you're operating at constant volume, then this factor will become zero. Okay. If you recall what was the uh, van der Waals equation, p plus a n square by v square, that into v minus nb. V minus nb, imagine I took it to the other side, nRT by V minus B. So from here I can write pressure is equal to nRT by V minus B minus A n square by V square. Okay, this is what we have. Okay. Now if at all I differentiate this with dP by dt at constant volume, so only I have to differentiate that with respect to T. So rest all will be constant. So this and this will be zero because there is no temperature term. Okay. So now if at all I substitute this back here, what would I get? nRT by V minus B minus P. P is what? P is nRT by V minus B plus a n square by V square. So you can see this factor, this will get cancelled and this will become a n square by V square. Clear? So the actual real gas equation for change of internal energy will be equal to delta U is equal to, I mean du is equal to ncv dt plus a n square by v square into dv. Correct? This is what it should be. Now tell me, if this equation is at constant volume, this factor will become 0. So which means du will be equal to ncv dt for real gas. So that means for real gas also we can get this equation ncv dt, but only at constant volume. Okay. But otherwise, if the volume is not constant, then we do not get this. Okay. I mean, then we do not get this value. We'll get this value. Okay. Clear on this point? Right. Now notice the last one. ncv dt is applicable for ideal gas at constant volume only. That means it is emphasizing that this is only valid for ideal gas. Is it only valid for ideal gas? Not necessary, right? Clear? This is not necessary. It is valid for even real gas also at constant volume. Are you getting this? So is this correct, beta? No, this is not correct. So what are the correct options? A, B, C. Ishman, I hope now you understood why the D is not correct, beta. Okay,
Yes, sir.
right. Others, please check. Any doubt here? Shall we go ahead? Right. Let's see the next question. So let us read the seventh one. We need to figure out the incorrect statements in this. Okay. Instead of correct, now we are worried about incorrect statements in this class. Let's talk about that. See, first one. dg is equal to vdp minus sdt is applicable for all the processes involving PV and non-PV work in a closed system. Okay. In case if you remember, we discussed this as dg is equal to vdp minus sdt plus dw non-expansive work. Correct? Any doubt? So, is this formula only for, you know, one which is involving PV work and non-expansive work, correct? Because if non-expansive work is involved, then I have to write this also into account. But is the equation given that way? No. So that means A is incorrect. A is incorrect statement. Clear? So it is for PV as well as non-PV. Both, if you have to represent both, then this is the correct formula. Okay. If you're writing only with only this one without this one, which means we are assuming that there is no non-PV work. Second one, B, delta S system cannot be negative in any adiabatic process in a closed system. Okay, in any adiabatic process in a closed system. That's a good question. I mean, that's a very good statement. Check it out. Delta S of the system, which is equal to Q reversible by T. Correct? Now, for reversible adiabatic process, you know that Q reversible is 0, which implies delta S of system is equal to 0. Now, you know that for irreversible adiabatic process, you know that Q irreversible is 0 because it is irreversible. Heat is supposed to be, I mean, the irreversible heat supposed to be 0. Correct? There is no heat exchange irreversibly. That means you know that delta S of the system is not defined for Q irreversible by T. This one is not correct. But delta S of surrounding is definitely defined for irreversible by T. Correct? But you know that since it is irreversible adiabatic process, any irreversible is a spontaneous process. So delta S of total has to be equal to delta S of system plus delta S of surrounding, and that must be greater than 0. Now, since Q irreversible is 0, this has to be 0 as well. Now, if this is 0, delta S of total has to be equal to delta S of the system, and that has to be greater than 0. So, what did we learn from here? So, delta S of the system has to be greater than 0 for adiabatic irreversible process or irreversible adiabatic process. Okay. So this is the conclusion we found, that delta S of the system is equal to 0 or delta S of the system is greater than 0. Correct? But it can never be negative. That means yes, the statement B is a correct statement. Clear, beta? Right. See the third one. du for the combustion of C6H6 gas in a sealed rigid diathermic container is 0. Okay. This is what it said. Now notice this. C6H6. So if at all we talk about C6H6 benzene, C6H6, okay, which is in a gaseous form, right, plus O2, that is giving CO2 gas plus H2O liquid. This is what you will get. Okay. Now, if you balance it, you will get this as, if you balance the points here, you will get this as 6 carbon dioxide here and 3 water molecules here. So 15 by 2 oxygens here. Got it? This is what is a balanced equation. Now, what is it being asked is delta U is equal to 0 for sealed and rigid diathermic container. Now, this is where it's to be understood one important thing about calorimetry. Calorimetry. Calorimetry says that if at all we are providing any heat, right? I mean, sorry, if heat is released during the combustion, heat released during combustion can be measured in two ways. One, keeping the volume constant. If the volume is constant and then you are measuring the heat, that calorimeter is called as bomb calorimeter. It is called bomb calorimeter. And in bomb calorimeter, whatever the heat that is being provided, I mean, whatever the heat that is being released during the reaction, it will only be increasing your internal energy because there is no work done here. So obviously, whatever the heat that is being released is saved into internal energy change. But if it is pressure constant, volume is not constant, but the pressure is constant. In that case, this is called as cup calorimeter. Cup calorimeter. So if it is cup calorimeter, then we can say whatever the heat that is released at constant pressure, that will be conserved at delta H. Okay. So therefore, here suppose for this reaction, if you are doing a combustion, combustion will always release energy. So energy will be released. And if you are releasing at constant volume, that will only change your internal energy. So it has to be less than 0. So will it be 0? No, right? So that means this is incorrect. So option C is incorrect. Clear? Next. Last one. I am van der Waal real gas in a critical condition subject to adiabatic free expansion experiences cooling effect. Okay, experiences cooling effect. Now, do you remember this something we discussed in gaseous state? In gaseous state, I discussed this point already. Let me remind you that. Okay, imagine this is a line. Okay, this is a line where Z is equal to 1. Got it? Now, this is a temperature line. At this temperature, which we call it as, inversion temperature. This is called inversion temperature. Above this temperature, what has been observed is that in case if you maintain the gases above its inversion temperature, inversion temperature, then what has been noticed is dt by dp, dt by dp at constant enthalpy here. That is what is defined as Joule Thomson Joule Thomson coefficient, mu of Jt, which is called Joule Thomson coefficient. This coefficient will be negative on expansion. What does that mean? If the gas is adiabatically expanding, correct? That means the pressure is decreasing. If pressure is decreasing, then temperature is increasing because above this inversion temperature, repulsive forces between the particles are more dominant. And because repulsive forces are dominant, Z is greater than 1. And when repulsive forces are dominant, particles will attain more amount of kinetic energy and they'll start increasing their temperature. Okay. So as the expansion increases, the particles will attain more energy because of the repulsion which they get, and they will increase the temperature. That's why this is being, you know, pressure is decreasing. So this is negative, but this is positive, and that makes it negative. But below the critical temperature, Joule Thomson's coefficient dou T by dou P at constant enthalpy is greater than 0, which means if the pressure is decreased, that means expansion is done, temperature will also decrease. And this is the basic fundamental we use for refrigeration. Okay, in all our refrigerators, there is a refrigerant gas, and that gas is working against the compressor in an adiabatic environment. Got it? So when it compresses, the compressor of refrigerator or a AC coolers, you know that they will have compressors in it. So gas will go and try to compress that. On compressing, what will it do? Compressing means it is expanding in the system. As it expands in the system, what should happen? Its temperature should fall down. Got it? So if this is negative and this is negative, that makes Joule-Thomson coefficient as positive. So this temperature here, cooling effect suggests that the interactions between the particles is actually decreasing. Interactions of the particles between the particles is increasing, which means they'll start having more attractive forces between them. Got it? because of which the cooling effect is observed. So remember, below the inversion temperature, cooling effect is observed. Above the inversion temperature, heating effect is observed. Heating effect is observed. So this is a concept which we discussed earlier in gaseous state. If you could recall, right now you attempt that for this question. See, a van der Waals gas in a critical condition subject to an adiabatic free expansion experiences a cooling effect. Yes, it will experiences a cooling effect. Why cooling effect? Notice, what is the critical temperature exactly? Remember what is critical temperature? Critical temperature is 8A by 27B. This is critical temperature, RB, sorry, 27 RB. What is Boyle's temperature? Boyle's temperature is A by RB. What is inversion temperature? Inversion temperature is always 2 times that of Boyle's temperature. Now, can you see that critical temperature is less than inversion temperature? That means you are below the inversion temperature. And below the inversion temperature, what effect is observed, everybody? Cooling effect is observed. Clear? Imagine if the same statement I tell you about this one, that uh, a, a van der Waals gas at, you know, 4 times the Boyle's temperature. If I tell you van der Waals gas is at 4 times the Boyle's temperature, and then it is subject to the free expansion, experiences cooling effect, then this will become wrong. Because if it is 4 times the Boyle's temperature, that means it is above the inversion temperature. And above the inversion temperature, heating effect is favorable. Clear? Please go through it now. Everybody, check it out. So what are the incorrect options here? A and C. A and C are the incorrect options. Clear? Just take a minute. Watch, try to understand all the statements. If there is any doubt, you can ask me. Let's discuss the 8th one. Right. Notice the 8th question now. An ideal gas is expanded so that amount of heat transfer to the gas is equal to the decrease in the enthalpy. Now choose the correct options. All the options have usual meaning. Okay, so please check it out. Molar heat capacity is equal to minus CPM. Molar heat capacity is given as minus CPM. Right, so check it out. First one, we start with the first one. What does it suggest? As for the first one, it is clearly mentioned that heats given at constant pressure, that will be equal to delta H, isn't it? Okay, heat transfer to the gas is equal to the decrease in its decrease, so minus delta H. And you know that NC delta T is how we represent Q, and that will be equal to minus NCP delta T. Correct? So molar heat capacity C will be equal to minus Cp. Okay, so that was given as option A. So this is correct. Option A is correct. Next, check out for option B. Okay, PV raised to power of 2 power gamma by gamma plus 1 is constant. Okay, now if you notice C, we can write it as Cm can be written as Cv plus R by 1 minus X. Correct? This is what we learned for polytropic process. Polytropic process. This is what we learned. Correct? And Cv can also be written as R by gamma minus 1. Okay? or let me derive that again. Clear? So I'll derive it once again. See, you know that Cp minus Cv is equal to R divided by Cp. You will get this as gamma minus 1 is equal to R by Cv. So that is, from here I can write Cv is equal to R by gamma minus 1. So therefore Cm is equal to R by gamma minus 1 plus R by 1 minus X. This is how you define it as C. Correct? So for polytropic process, correct, if at all I have to write this in terms of R, this is how much you will be. Correct? And now what is it been written? Hmm. Now since C is equal to Cp, C is equal to minus Cp, let me write down that as minus Cp here. So minus Cp will be equal to R by gamma minus 1 plus R by 1 minus X. This is what you will get. Correct? But we also know that Cp minus Cv is equal to gamma. Cp minus Cv is equal to gamma. So we require to write in PV raised to power of gamma. Okay. Hmm. So I need to find out n from here. Okay. Hmm. So I don't think this much is required for us to do. One second. I'll do it even more easily. Sorry. Let me redo that because CP is already given to us, so we don't have to do so much. We just need to calculate this X value, so that becomes easier for us. So we know that CP is given as CM is given as minus CP minus CV minus CP is equal to CV plus R by 1 minus X. Okay. And if I take this CV to the other side here, so I will get this as minus of minus of Cp plus Cv is equal to R by 1 minus X. Got it? And now we know that Cp can be written as Cp by gamma. We know that Cp minus Cv is equal to R, and Cv can be written as R by gamma minus 1. What about Cp? Because Cp is equal to Cv plus R, I can write this as Cv is R by gamma minus 1 plus R. So that makes it gamma R by gamma minus 1. So just use these factors here. So minus of, we can write this as R gamma by gamma minus 1 plus R by gamma minus 1. That is equal to R by 1 minus X. So now you can see R will get cancelled from here. Okay. Once R will get cancelled, I will get this as 1 plus gamma. So this is minus of 1 plus gamma by 1 minus gamma. Correct? That is equal to 1 by 1 minus X. So reverse this value. So I'll get this as 1 minus X is equal to 1 plus gamma by gamma minus 1. I can write it as this way. Or simply 1 plus gamma, I can write it as 1 plus gamma, I can write it as gamma plus 1 by gamma minus 1. Okay. So from here, X can be written as 1 minus gamma plus 1 by gamma minus 1. So gamma minus gamma minus 1 by gamma minus 1. So that makes it gamma will get cancelled. So minus 2 by gamma minus 1. Clear? Minus 2 by gamma minus 1. So gamma minus 1. We're not getting exactly the same value. 2 gamma, I have to get 2 gamma also. Hmm. Let me see if at all I did any mistake there. CV is equal to R by gamma minus 1. and yeah, Cp is equal to Cv plus R. So R by gamma minus 1 plus R. So this is coming out to be R gamma by gamma minus 1. And if I bring it to the left hand side, it will become minus Cv. So minus will come common. So R, and this is gamma minus 1. Uh, oh, sorry, here I made a mistake. So let me rewrite this part. Yeah, while taking LCM, I made a mistake. R will get cancelled off. So I will get this as, uh, gamma plus 1 by gamma minus 1. No, I did it correct only then. Gamma plus 1 plus gamma minus 1. That is equal to 1 by 1 minus x. So if I take this minus on the other side, I'll get 1 by x minus 1. So this can be removed out. So 1 by x minus 1. So x minus 1 is equal to gamma minus 1 plus gamma plus 1. Gamma plus 1, yeah. And now we should get gamma minus 1 by gamma plus 1 plus 1. So that is equal to gamma minus 1 plus gamma plus 1 divided by gamma plus 1. Yeah, now we are getting it. So x is equal to 2 gamma by gamma plus 1. So this is the value of x. So now tell me, for a polytropic process, what do we write? PV raised to power of x is equal to constant. So what is PV raised to power of x? 2 gamma by gamma plus 1. So that is equal to constant. And so this is option B. So I think we got that. Please check. Is the calculation part clear, everybody? Please do check. C is also correct, since TV raised to power of x minus 1 is equal to constant. X minus 1 is already something we got it. X minus 1 is gamma minus 1 by gamma plus 1. So that is equal to constant. So C is also correct. So A, B, C. These three are correct statements. Please check. Everyone, did you get this? Right. Let's talk about the ninth one now. Please check. A cyclic process of 1 mole of monoatomic gas is given in PT diagram. Choose the following option. Okay. P versus T is given. So it is going from A to B, B to C, then C to A. A to B is isobaric process, B to C is isochoric process, C to A is some polytropic process. C to A is some polytropic process. Clear? Based on that, we need to find out first A to B what is the work done, and internal energy change from B to C. And for a cyclic process, we know that delta H, we know that total work done. So W of the total work done. And C to A, how much is the heat given? That is what we need to figure out. Clear? So let's see how we can calculate one by one here. Check out. First one, I need to find out the work done from A to B. Okay. So we'll go option by option. So if you notice the first option, AB is an isobaric process. Isobaric process. Clear? Let me start writing from the right hand side so that you can see that as well at the same time. Check. So this is an isobaric process. So work done will be equal to minus P into delta V, correct? P delta V can be written as minus NR delta T. And since this is between pressure and temperature, oh, sorry, this is temperature. So this BC is isothermal process, okay? So work done will be equal to minus NR into T2 minus T1, correct? So that is equal to 1 mole into R into temperature is 546 minus 273. So that is again 273 only. So minus R into 273, correct? So the first option is correct. So this is about A option. Let's talk about the B option solution now. Change in internal energy between B to C. Have you noticed something? B to C is isothermal process. Delta T will be 0. It is isothermal. Isothermal process for B to C. So therefore delta U will also be 0. So that is also sorted. So B is incorrect. Next, check out C. Complete cyclic process delta U is equal to 0. This much is 0. And work done will be equal to this plus this. Okay. Work done we usually figure out only by checking out the area under the curve. Correct. So area under the curve, how much that is being given here. Uh, so you can see how you can calculate. Yeah. This is the work done and it is an anti-clockwise direction. I hope you guys understood that it is in an anti-clockwise direction. Hmm. Oh, sorry. You can see this one also. This is pressure versus temperature graph where it is passing through origin. That means it is at constant volume, Gay-Lussac's law. This is at constant volume, which means work done in this process and this process will be same as the area under this curve. So therefore, work done uh, net will be equal to work of AB plus BC plus CA. CA is 0 because it is at constant volume. So work done AB we calculated already. Now work done BC. BC is an isothermal process. For an isothermal process, what is the formula? Minus 2.303 nRT log of V2 by V1 or minus 2.303 nRT ln P1 by P2. So that is ln P1 by P2. So that is equal to minus 2.303 nRT log of, not ln, log of P1 by P2. P1 is 1 by 2. Okay, this is what you will have, correct? So therefore, total work done will be equal to WAB plus WBC, which is equal to minus of, we got this as minus of 273R minus 273R plus 2 point, I mean, obviously this will also be minus. So minus 2.303 RT log of 1 by 2. Okay. And T being temperature at this particular value, you know how much it is? B to C. Temperature is 546. So that into 546 times of log of 1 by 2. This is what it should be. Correct. But you see, this formula is not coming out exactly correct. Check it out. Clear? So C is also incorrect. Next, D. Heat addition along path CA. CA, how much amount of heat is been added? See, this is the amount of heat. Sorry, across CA. CA, we will have to check because work done is 0 here. W of CA is 0. CA is 0. Then delta U will be equal to Q of CA. So QCA is equal to delta U, which is equal to NCV TC minus TA. Correct? I mean TA minus TC. TA minus TC. So that is equal to 1 into CV and it is a monoatomic gas, right? So therefore 3 by 2 R. So it is 3 by 2 R into A. A temperature is 273 minus C. C temperature is 546. 546. So that is equal to 3 by 2 R into minus 273. Correct? So this much. See the option here. That is what is given. Minus 3R by 2 into 273 joules. Correct? Or whatever the units are. So C is correct here. Please notice. Any doubt in the question, let me know. Finished? Right. Notice the 10th one now. For the process H2O liquid to H2O gas, what are the points here which are correct? Delta G will be 0 if vapor pressure of H2O at T kelvins is given. Correct? So this temperature, if it is at same, and P bar is given, if P is equal to vapor pressure of H2O, then delta G will be equal to 0. Is this correct or not? That is what we need to check. Right. So check out. Okay. Now let's notice this, everybody. See what we can say. H2O liquid, it is in equilibrium with H2O. I mean, this is in reversible with H2O gas. Right. This is at P bar. I mean, total system is at P bar here. This is all at P bar. Okay. If P is equal to vapor pressure of H2O, vapor pressure of H2O, okay, then what will happen? Remember what is boiling point, everybody? What is the definition of boiling point? Boiling point temperature is that when the vapor pressure of the liquid is equal to external pressure or pressure of the atmosphere or atmospheric pressure. Clear? So PATM. So yes, the first option seems to be correct because at this point we will have, if the temperature at this temperature T, vapor pressure of the liquid is equal to pressure of the atmosphere, that means the boiling has started. At boiling point you will see the equilibrium exist between liquid and gas. There is an equilibrium existing. So when equilibrium exists, delta G will be equal to 0 because the uh, delta G will be 0 at boiling point, of liquid. Okay. So this A seems to be right. Next, if pressure, if vapor pressure of the water is, if P is equal to vapor pressure of H2O liquid at temperature above T kelvins. Okay. If this is above T kelvins, then we are meeting this one. Okay. So notice the statement carefully here. So what is said? If pressure of the, if the vapor, if P is the vapor pressure of water at temperature above the T kelvins, we learned that boiling point is T kelvins. Boiling point is T kelvins. Let's say for water it is 100, 373 kelvins, which is 373 kelvins. Clear? Now, if the boiling point is reaching only when it is above T temperature, so that means if the vapor pressure of H2O, clear, is equal to P of ATM, pressure of ATM, correct? P of ATM at temperature T, which is greater than boiling point. This is the condition which is given. Okay. This is only happening at temperature T. So which means, can I say that these two are becoming vapor pressure of PATM is becoming H2O just above the boiling point. Let's say these two are happening to be at, let's say, 105 degrees Celsius. Correct? So let's say 105 degrees Celsius or 378 kelvins. If this is a temperature given. Okay. So if this is the case, what happens to the delta G? What happens to the delta G for this equation now? Okay, will it be in the backward direction or will it be in the forward direction? Okay. Now tell me, uh, let me put it this way in a simple example. Got it? If you notice, when would this happen? See, if the uh, okay, let me take one simple example and explain. Suppose if you are in the kitchen and you are trying to boil water, you know, maximum amount of temperature the water can reach is 100 degrees. Imagine it is open vessel. That is the maximum amount of temperature the liquid water can attain. Because beyond that, everything will start vaporizing, isn't it? Because that is a boiling point. What will be the same boiling point when you are, you know, somewhere in the Himalayas? We are at an altitude now, correct? Let's say you went to Kedarnath. Okay, Kedarnath is around 3,700 kilometers meters above from the sea level, correct? So in that case, on Kedarnath, when you are boiling water, correct? You know what is the boiling point of water at that particular at Kedarnath? It will not be 100 degrees. It will be around 90 degrees only. Why is that? Because the external pressure, which is the atmospheric pressure, is not 1 atm. It is less than 1 atm. Got it? So to reach that 1 atm, to reach that external pressure, you do not require that high amount of temperature. You do not reach to need to go to the 100 degrees centigrade. Okay, that's one of the reasons why, you know, pressure cookers are more important to boil dal and, you know, anything which is more heavier to break down. Clear? Especially at Himalaya regions. Got it? But think about the alternative also. Suppose if you are in a submarine somewhere, correct, where the pressure is high, external pressure is high now. Okay, now will the water boil at 100 degrees? No, right? No, the water doesn't boil at 100 degrees. Is the point clear, everybody? Which means to reach that same external pressure, you require to spill more amount of temperature. So at 100 degrees, reaction would still be more on the backward direction and not in the forward direction. It will be more in the liquid region and less will be in the vapor region, isn't it? So overall, the net reaction is more backward and not more forward. Is that making sense? Right? So which means, yes, this option is also correct. That is, if the reaction is more backward, that it is non-spontaneous and delta G value will be positive. Clear? Next. Next one. Delta G is equal to positive if P is greater than the vapor pressure at T. That is what we are talking about. Yes, so this is also correct. And delta G will be negative if P is less than the vapor pressure of the H2O at this one. This is also correct. Clear? Everybody understood what I'm trying to say? Any doubt? Right. Let's see the next one. Three moles of an ideal gas is subject to the following change in the state. Identify the correct statement. State A to state B to state C and to state D. Okay. So if these are the values given, so you need to figure out A, B, C, D here. So let's see one by one. What are we doing? Reversible isobaric cooling. Reversible isobaric cooling. That means the pressure is same here. Okay. Pressure is same. And we are talking about ideal gas only. Right. So in that case, from this temperature and pressure with this number of moles, if you are operating, keeping the pressure constant, so here PB will be same as that of 2 2 bar. Here this will be 2 bar only. Got it? So from the A value, what can we say here? Now, Acha, he didn't ask anything in the A value here. So directly we are checking out on this position here. Now, here reversible isothermal expansion is being done and temperature now is 300 kelvin. So which is an indication that this is also 300 kelvins, isn't it? Make sense? So the first statement is correct. TB temperature and T, no, TD temperature is said. Sorry. A is not correct. You need to check out TD also. Okay. So far we found that TB is equal to TC, which is equal to 300 kelvins. Now there is adiabatic free expansion. Acha. In free expansion, there is no change in temperature. So that is also correct. So TB is equal to TC is equal to TD is equal to 300 kelvins. So this is correct now. For free expansion, delta T is 0. Okay. Next. Delta H of A to D. A to D, what is the temperature change here, beta? D is 300. So delta H of A to D, delta H of A to D will be equal to NCP delta T. So 3 into Cp value is gamma is 5 by 3. 5 by 3 means it is monoatomic. So 5 by 2 R into T2 minus T1. T2 is 300 minus 400. Okay. So that is equal to 3 times of 5 by 2 R into 100. Clear? I guess that is clear. So this is coming out to be 750 R. Right? Sorry, minus with minus value. So this will be minus 750 R. Done? Right. So this is coming out to be wrong. Why? Because it should be minus, it is given as plus. Next. A to C. Check out from A to C. A to C. See, pressure is also changing. Temperature is also changing. So we have to apply these two factors here. So check out. Delta S, what is the formula we learned? NCV ln T2 by T1 plus NR ln V2 by V1. So let me put this as V2 by V1 in terms of pressure also. So we know that P2 V2 is equal to NR T2, P1 V1 is equal to NR T1. So we can write V2 by V1 is equal to T2 by T1 into P1 by P2. So if I substitute that here, so what do I get? NCV ln T2 by T1 plus NR ln. I can write it as again T2 by T1 plus NR ln P1 by P2, correct? So you notice this one. This entire factor is same. This is like CV plus R. CV plus R can be written as CP. So NCP ln T2 by T1 plus NR ln P1 by P2. This is another way of remembering the formula. Sometimes this formula is more useful for solving rather than this formula. Okay. So now let us apply that. Delta S is equal to 3 times of Cp is 5 by 2 R into ln T2 by T1. T2 is how much? Final temperature is 300, initially is 400. So 300 by 400 plus 3 times of R into ln P1. Originally we had 2 bar, now it is 1 bar. So 2 by 1. So that is equal to 3R minus, 3R ln 2, 3R ln 2 minus 15 by 2 ln 4 by 3. Correct? So I can write it as 4 by 3 here. Right? So now after working out whether this will be 0 or not, that is what we need to check. Is it coming out to be 0? No, right? This is non-zero. You can see this is not equal. So therefore, this one is also wrong. Okay. Last one, internal energy change. Delta E means internal energy change between B to D. Acha, B to D, is there any temperature change? No change. Same temperature. So therefore, delta U of B to D or delta E of B to D, that is one and the same, that has to be equal to 0 as delta T is 0. So this factor is correct. So A and D are correct answers. Please check. Everyone clear on that?